Hello again. So, local area network, a set of devices that are connected at the MAC layer. Already we have seen this. Another property of the local area network, also we have seen this. So all machines that are connected to the same MAC layer should share the same network prefix. So here we have the numbers in red are the same for all these machines that are connected to the same LAN. Here the numbers in green are also the same for all these machines connected together. Now, how MAC and IP interact? And now I will answer the question that I had about the IP address in the previous slide. Now, actually, let us see what we have. This machine S is sending a packet to D. S will look at S forwarding table. So here it is not a router, so the forwarding table has only two entries. One entry for the local area network, which shows the network prefix, and it mentioned that this destination is directly connected to the machine. And the next entry is the default gateway. So the destination address of D is this one. There's no match with the first entry. Now, so in this case, S has no other choice than sending this packet to the default gateway, which is the one of the router. So at the IP layer, at the network layer, the destination of the packet is D. It will not change. But at the MAC layer, the destination of this packet is the router. So the destination MAC address should be the one of the router, so that the router can receive the packet and deliver it to the IP layer. But the destination IP address of this packet is D and will not change because we are moving from one LAN to another. And again here, the router will forward the packet to D. So the destination IP address will remain the same. The source IP address again remains the same as the one of the original sender, which is S, but the destination MAC address is the one that will receive the packet on this LAN, which is D. So now in this case, we have the destination MAC address and the destination MAC, the destination IP address corresponds to D in this LAN, but in this LAN, it was not the case. Network mask. So I talked a lot about network prefix. Actually, network, and now this is another way to identify the network prefix of a given IP address. So one way to know the length, the size of the network prefix is simply by writing the IP address slash some number here. This number indicates the length of the network prefix. 21 means that the network prefix is corresponds to the first 21 bits of this IP address. Now, if the network prefix corresponds to the completely to the first byte, instead of 21, we should have 24, for example. Yeah, 24. 24 means that the first 24 bits, which corresponds to the first byte. And this number is variable, it's not fixed. So for a given LAN is fixed, but at TPFL, we use 24. In other companies, intranet, you might use 28, 29, and might use 31. 31 is a bit, extreme, but this number is variable. Now, with this representation, we are able to know the length of the network prefix and the network prefix as well. There's another representation to know the network prefix is using the network mask. The network mask is nothing but we take the IP address, we take the first the bits that corresponds to the network prefix, we set all of them to 1, and we set the remaining to 0. And this gives us the net mask of a given IP address. So in this case, the net mask for this IP address is the 255.248.0. Address resolution, ARP, actually, okay. So assume that you have a packet. You want to send this packet to another machine on the same LAN. You know the IP address of this machine, but you don't know the MAC address. So you are not able to send this packet on the LAN unless you resolve the MAC address of the destination on the same LAN. So this is why we have what we call the address resolution protocol. What happens? We have this machine has a packet to send to this machine. The AD2 needs to send a packet to ST-SUN1. So what it does, it sends a request with the destination MAC address being the broadcast MAC address by setting all bits to 1. And this packet will be received, this frame will be received by all machines connecting to the same LAN, by all machines that are hearing this packet. Now, inside this packet, we have the question, who has this IP address? So, and then only the machine that has the corresponding IP address will reply, will send an ARP reply, and that way, this machine is able to receive the ARP reply. It finds within this ARP reply the MAC address of the destination that it needs to communicate with, and at that moment it will be able to send the IP packet that it has, which will be in step 3. So step 1. ARP request to know who has this IP address. Step 2, to the ARP reply, I have this IP address and this is my MAC address. Step 3, it sends the packet with the right IP address and with the right MAC address. Now this is the physical layer, it's just the way that we transform bits into a physical signal. It's not, it's not a part of the scope of this crash course, because in this course we focus on the protocols, we don't focus on the physical channel, but just to give you an idea. Now let us put everything together. We have a web browser which is sending a file to Elaine. So now we'll try to analyze a bit how things are going between the web browser, switch, router, and Elaine's. Here we have the web browser. The web browser is sending a packet. The packet will go through the interface between the application and the transport simply by just the send command that will deliver the whole data to the transport layer. And then the transport layer will deliver this communication service to the application and will put the data in a format that can, allows this data to be transferred on the network. So the file is segmented, is packetized into 5 different segments. Every segment has some small header that does not appear here. This header indicates the source and port, the source and destination port numbers, the numbers that identifies the application on top of the transport layer, and also within the transport header we have other control information. Now from the transport to the network layer, we have what we call encapsulation. So we take the segment, we add the IP header, and as we can see, inside this IP header is green because it corresponds to the, it has the destination IP address being the one of Elaine, because the scope of the network layer is the whole network, is the end-to-end. This is why here we have green, and then we take these packets to the MAC layer, and also we have another encapsulation where we add the MAC header. Now in the IP header, we have the source IP address of the web browser, we have the destination MAC address, the destination IP address of Elaine. At the MAC layer, the source MAC address will be the one of the web browser, and the destination MAC address will be the one of the router. And again, the scope of the MAC layer is only the local area network. It has not any visibility about what's happening beyond this local area network, and it does not carry any information that helps forwarding the packet beyond this local area network. This is why we see here the red header that corresponds only to this limit, which is the router. Now, this is the physical channel. The physical layer will provide the data from physical signal to bits. Then the MAC layer will look at the destination MAC address. It corresponds to the router MAC address. It will take the frame, decapsulate it, and deliver the IP packet to the IP layer. The IP layer will look at the destination IP address. It will look at this address inside its forwarding table. It decides to forward the packet to Elaine. Again, we have another encapsulation of the IP address at the MAC layer, and this time the MAC layer scope is between the router and Elaine. The MAC address, the source MAC address is the one of the router, and is not anymore the one of the web browser, and the destination MAC address will be the one of Elaine, which is the next hop on the same LAN. So the MAC layer receives the frames, it verifies, it checks the destination MAC address, it corresponds to the local MAC address of Elaine, decapsulate the frame to obtain the IP packets that are delivered to the IP packet. Elaine verifies the destination IP address, it corresponds to its IP address. The IP packets delivered to the transport layer. The transport layer will put the data together and put them in a buffer, and the application will retrieve this data in a pool mode. Now we have some terminology because I was using a segment packet frame. Actually, I was doing that on purpose because the transport layer we say segment. Especially with TCP, we call TCP segment. With IP, we call IP packet, and with MAC, we call MAC frame. So MAC frame, IP packet, TCP segment. The onion view. So here we have the MAC frame. In the MAC frame, we have the MAC header, where we have the MAC addresses and other control fields. So before here, is this the payload of the MAC frame? The payload of the MAC frame is nothing but the IP packet. Within the IP packet, we have again the IP header, where we have the source and destination IP addresses and other things. And we have the payload. Again, the IP payload is nothing but the TCP segment. The TCP segment, we have the TCP header and the TCP payload. The TCP payload is the application data. In this case, in our case, of the web browser, is the base of an HTML file. Here we have a nice display of a packet. So here we use a sniffing tool that take the data and just show them in a nice way. So here we can see the MAC, the Ethernet header. It's the MAC header. We can see the source MAC address. We can see the destination MAC address. Cisco indicates the manufacturer of the code of the destination. So this is something that we can read from the first bits of the MAC address. Western Digital is the manufacturer of the adapter using this MAC address. And here we see the protocol that is above the MAC layer is the IP, is 0800, which indicates the IP protocol. In the IP header, again, we can see the source IP address. Again, we can see the destination IP address. Also, we see the TTL or the hop limit. Let us see where it is. Here we have the time to live is 64 by default. Seconds is historical, so actually it should be hops, 64 hops. And then here we have the TCP header that have the port number. The source port number is 1268, and the destination port number is 23, which indicates the Internet application. Now we have a poll again. We observe a packet from the web server to Elaine. At the observation point 1, say what's true. Five seconds. I close the poll. So the majority is correct. So the first point is that the destination MAC address is the MAC address of the router. Was correct because the MAC address indicates the next hop on the same LAN. The second point, the destination IP address is the IP address of the router is wrong because the destination IP address indicates always the address of the endpoint, because the scope of the IP layer is the whole network is end-to-end, but the scope of the MAC layer is only one device to the second device within the same LAN. Now, PMU to PTC communication. Let us move to the smart grid. So PMU is the phasor measurement unit. PDC is the phasor data concentrator. We have PMU1 sends a packet to PDC. At time 0, PMU knows only the name of PDC, does not know anything about its IP address or what's happening in the network, or all cache in the network are empty. And now PMU-A wants to send a packet to PDC. At time T, we see a packet X at switch 1. This is the very first packet. So the very first packet, here we observe the packet that's sent by A at switch 1, and the purpose of A originally is to communicate with PDC. Now, what type of packet is X? Paul? Five seconds. I close the poll. Actually, the co-majority of ARP is correct. Actually, let us think about it. PMU knows the name of PDC. So the first thing to do, it needs to resolve the name to get the IP address. So it needs to send a packet to the DNS, asking the DNS, what is the IP address of this name of the PDC? So it will look at in its forwarding table, it will see that the DNS does not share the same network prefix. So the DNS is on another LAN, so it needs to go through the router. But the issue is that to be able to go to the router, it needs to know the MAC address of the router. Otherwise, the router will simply ignore the packet. So the first packet it needs to do, the first thing it needs to do is to send an ARP request on the local LAN, or the local area network, asking who has the IP address of the router. And then the router will hear it, will get it, and will reply with its by its MAC address. So the first packet that we can see on the network is ARP request. Second question, at time T0, we see a packet P0 at switch 1. This packet was sent by PMUA right after it received a reply from the ARP packet. Okay, so here we sent ARP, R1 answered with its MAC. Just after we see a packet at switch 1. What kind of packet it is? So what application does the packet does the data transported in P0 belong to? Paul? So thank you to Stefan. He's helping me with the polls.
Can you just get back to the previous slide to see just the condition?
This one? Sure.
Yeah. Okay. Thank you. Thank you.
So all what has been done so far is that PMU got the MAC address of R1. So it's able to send a packet as a next distance to R1 that can be received by R1 on the same LAN. 5 seconds. I close the poll. So the right answer is DNS. Why? Because as I said before, the PMU knows only the name of the PDC. It does not know its IP address. To be able to communicate with the PDC, it needs to know its IP address. So what it needs to do first, so it has to send a DNS request, a DNS to the DNS server, asking who has this name. The DNS server will reply with the IP address of the PDC. And the ARP, the previous ARP was to resolve the MAC address of R1 to be able to send the packet to R1 so that it interconnects this LAN with this LAN. So that it can forward the DNS request from PMU A to the DNS. What protocol does the P0 transport layer header belong to? Paul? This is something that we have not seen yet in the slides, so I think you need to guess which of the protocol we use with DNS. 5 seconds. I close the poll, and the majority says UDP, which is correct, because with DNS, the request and reply are very short messages. And if you would like to use TCP, it comes with a huge overhead, and it is not worth it to use TCP with DNS request. What is the source IP address destination? What, yeah, in P0. What is the source IP address, destination IP address in P0? So again, we have a message sent by PMUA to DNS. So we can start the poll right now. So we have a message going from PMUA to the DNS, and we are looking at this message at switch 1. What's the IP address? What is the source IP address and the destination IP address of this packet that is intercepted at switch 1? Five seconds. I close the poll. The right answer is 1. Why? So this is a DNS request, and this is a message that's sent between PMUA and the DNS. So the final destination of this packet is the DNS. So the destination IP address should be the one of the DNS. And given that it is sent, the source of this message, the PMUA, so the IP address of the the source IP address should be the one of PMUA. So finally, the first answer was the correct one. Again, why? Because this message, the end-to-end of the DNS request, is the PMUA and the DNS. So the message is between these two machines, and the message should carry the IP address of these two machines. It depends on the direction where it's going. What is the source MAC address, destination MAC address in P0? So the same message going from PMU to DNS, and we are looking at this message at switch 1, and what are the source MAC address this time and the destination MAC address? Paul?
What do you mean by P0?
P0 is the packet that's sent from PMUA to DNS. It's the DNS request. So P0 is the packet that's asking the DNS, that's going from PMU to the DNS, asking to resolve the name of the PDC. So here we have a packet going through the router to the DNS. Again, to help you, the MAC layer, the scope of the MAC layer is the local area network, and the scope of the IP layer is the whole network. And here we talk about the MAC layer. Five seconds. I close the poll. So the right answer is that the majority is correct this time as well. So the right answer is that the source MAC address corresponds to PMUA, and the destination MAC address corresponds to the next hop within this LAN, which correspond to the router R1. MAC address, the switch is transparent. So it's transparent in this communication.
Just what is the purpose of the switch? It's not very clear for me.
The purpose of the switch is to isolate the collision domain. So if you don't have a switch here, you will have one line. On this line, you have all the machines connecting to each other. So in that way, so we need to arbitrate among the different machines, and the bandwidth of the link is reduced. So in order to avoid collisions, we put a switch. So every machine is connected on one port on the switch, and the switch will do the dispatching on other ports.
Okay.
So it is here just to isolate the collision domain within one LAN.
Kind of regulating the traffic, but doesn't interfere on the...
It does not need really to regulate the traffic, but just it avoids the collision, because now the communication between this machine and the router, first of all, to go from this machine to the switch, on the port on the switch, there's no collisions because it is how say full duplex. And then the switch, actually it is a learning switch. It's some kind of smart switch. It has a cache where it remembers which MAC address is connected to which port. So it looks at its cache. It sees that the destination MAC address is connected to this port, and will dispatch, will forward the packet to this port to the router.
Okay.
But it is completely transparent, and the goal of the switch is just to split the one collision domain that you might have if you have only one cable between all machines.
Okay.
And historically, we had one collision domain. It was only one cable connecting all these machines together.
Thank you.
Most welcome. So the DNS server replies with the address of PDC as 10.2.1.1. So at time T1 larger than T0, we see a packet P1. So now we are looking for a packet P1 at the interface of the router, the western interface of the router R1. This is a data packet that consists of the phaser information. So now we have the phaser, the PMU is sending data to PDC. And we intercept the packet at the western interface of router R1. So PMU is sending a data to PDC because now it has the IP address of PDC, is able to communicate directly with the PDC, and it's a data. It's a packet carrying data, and we are here. We are looking at the packet here. What application does the data transported in P1 belong to? Paul? Five seconds. I close the poll. Okay, so the right answer is the IEC something. Actually, the phaser is sending its data. Data it's collecting. It's not sending. It's not sending HTTP data. So it's not a web client. It's not a web server. So it has its own protocol. It has the an agreed protocol between the phaser and the concentrator. And this protocol is the IEC one. So it's not HTTP, because here we're not talking about web browser, about web server or web client. It's not TCP, because TCP is not an application. TCP is a transport layer. It's not DNS because again, it is the information that is acquired by the phaser that needs to send to BDC, and DNS is used for resolving IP addresses.
I thought we said it. Oh, maybe it's the next question.
Sorry?
I thought we said UDP, that it communicates with UDP because
yeah, UDP is transport layer, it's not application layer. The
okay.
question is about application.
Okay, yeah, totally right.
Okay, so yeah, we need really to be careful about all these small things. It's not very easy to remember everything together. What protocol does the P1 transport layer header belong to? Okay, now that was your question, Paul. Okay, 5 seconds. I will end the poll, share the result, and the right answer is UDP. That's what we have seen at the early beginning of the lecture of today. So UDP, because to avoid the head of line problem issue with TCP. Although TCP is reliable, but it might create extra delays that violate the real-time constraint that we have with the communication between the PMU and the PDC. That's why we use UDP. What is the source IP address, destination IP address in P1? So we have a packet that's sent from PMUA to PDC. We are looking at this packet at this point, the western port of R1. What are the source IP address, destination IP address? Paul. So again, remember the scope of the IP layer is the whole network, and the scope of the MAC layer is the local network. Five seconds. I close the poll. Okay, and the majority is right. So we have this tuple here. So the source IP address corresponds to the PMU, the source that's of the message. The destination IP address corresponds to the final destination of the message, which is the PDC. What's the source MAC address, destination MAC address in P1? So we have a packet sent by PMUA to PDC. We are intercepting this packet at this point. What are the source MAC address and the destination MAC address? Paul. Again, the network layer is, the scope of the network layer is the whole network, and the scope of the MAC layer is the local network. Five seconds. I will close the poll, share results, and again, the majority is right. So the MAC address, we look only at the local area network. With this local area network, the source MAC address is the one that injects the packet inside this local area network, and the destination MAC address is the one that will receive the packet within the same local area network. So the source is PMUA and the destination is the interface of R1 on this LAN. Which of the following forwarding tables at R1 are valid? So check whether they allow P1 to reach the PDC. So again, a packet going from PMUA to PDC. We are at R1, we have a forwarding table. We propose 4 forwarding tables. Which of them are valid? So I suggest you to look which one is able to route the packet to the right, which one of them is able to route the packet P1 to the right next hop. Five seconds. I close the poll. I share the results. Yeah. So fortunately, I had at least one who answered with the right answer. Okay, surely the good answer is number 4, BCD. Why? This is the forwarding table A. So the packet is going to this destination. So it's 10.211. If we look at the forwarding table, we have a match here, only the first entry. And the first entry, this is the north, the entry that indicates that to the packet to go to the DNS. So that's wrong. So this will not work, it will not forward the packet to the next hop. So because now we expect that R1 will forward the packet to R2. And with this forwarding table, the packet will be forwarded to the DNS, and it's wrong. Second table. So we don't have much with the first entry. We don't have much with the second entry. We have the default gateway. And the default gateway says that the packet should go to the east, which is true because this is where we need to forward the packet. So the packet needs to go to the east to R2 so that then R2 will hopefully has the right hopefully has the right forwarding table to forward the packet to PDC. So this one is correct because this allows R1 to forward the packet to R2. So B is correct. Forwarding table C. So we don't have a match with the first entry. We don't have a match with the second entry. But with the third entry, we need to think about it. So let us transform it into bits to see whether we have a match or not. So the 10.0/13 corresponds to this prefix. Let us see let us transform the IP address of PDC into bits to see whether they match. So this is the IP address of the PDC, and we see that we have a match here. And again, if we would like to go to look further, we can take also the IP address of the SCADA here to see whether we have a match and whether it will be forward packets that are distant to SCADA will be forwarded well by R1. So we take this IP address, we put it here, the one of the SCADA, we transform it into binary, and then also we have a match. So now we are sure that the packet P1 that's going to PDC will be forwarded to east to R2, which is correct, and also packets that are going to the SCADA will be forwarded to R2 to the east, which is correct. So this means that the forwarding table C is as well correct. Now the last table D, we don't have a match with the first entry because here we have 10.2, here we have 10.10, we have 10.1. Also, we don't have a match with the second entry, we don't have a match with the third entry, but we have a match with the fourth entry, which is 10.2.16. And this one is indicating to go west. Okay, that's a typo because it should be east, not west. Okay, so for, yeah, now I understand that the divergence. So D is not correct, because it should be east, so D is not correct. So that's not the right answer, and none of them is the right answer. So the right answer is only B and C.
Right answer is 5.
The answer is, yes, you're right, that is 5. Okay, we have a right answer, correct answer in the end.
Why is A not valid?
A not valid, okay, because I will again A. Because we have a match with this entry, and this entry is stating that to go to the north, and the north is the DNS. You see what I mean?
Yeah, and the DNS does not have the same IP address.
Exactly, and yeah, so the packet that's going to the PDC will be forwarded to the DNS, and it's not really the right destination. So the router is responsible for forwarding the packet to the right destination. So the packet should go to the PDC. So if it sends the packet to the DNS, DNS is not a router. There's no way that the DNS will forward the packet to the PDC.
But what is the meaning of the /8?
/8 is, yeah, it is the network prefix length. This is what we have seen with the net mask. So this the network prefix length, exactly, size. This means that we have number 10. That number 10 is the first byte of an IP address, and the whole byte is the prefix, the network prefix. Because remember that the IP address is over 32 bits. The network prefix indicates the networks to which the machine is connected. But sometimes we have some kind of aggregation. But yeah, so here we have 10. We look at 10 with the only 8 bits. We look at the only 8 bits of the number 10. We compare it with the 8 bits, the first 8 bits of this IP address here, and to see whether there's a match or not. In this case, we have 10 here and 10 here, so there's a match. So since there's a match, the packet will be forwarded to the north actually, and this is wrong.
Yeah, get it. Thank you.
Okay. I think, yes, so we'll stop here. So thank you very much. So now you still have to do the quiz, and you can start the lab this week, and see you next week. And actually, see you on Friday. Have a nice day. Bye.
Sorry,
Thank you. Bye.
Quick question.
Yeah, sure.
Just once it arrives to R2 with the forwarding table, you will use the MAC, right, to do it from R2 to PDC, right?
No, R2 is another router. So here we have a router. The router is connected to another router through a LAN. Here it's a LAN, although we have only 2 interfaces connected to it, but this is a LAN. And the router acts as the third layer. So the router will look at the destination IP address to decide where to send the packet. This router is connected to 3 different LANs. One LAN is here. These devices are connected at the MAC layer. Another LAN is here. We have only 1 device. Third line is here. We have this is the LAN that's between this router and this router. So this one will receive the packet. It will forward it to R2. But now this packet that's between R1 and R2 has the source IP address, the one of PMUA, has the destination IP address, the one of PDC. But at the MAC layer, the source MAC address is the one of R1, and the destination MAC address is the one of R2. The MAC layer, the scope of the MAC layer is the local area network, and the scope of the IP layer is the whole network. So this one will receive the packet. It will forward it to the right destination. It will keep the source destination IP address the same. It will not alter the source destination IP address, but it will change the MAC addresses. So within this LAN, the frames is going from this machine to this machine. So the frame should carry the MAC address of R2 as the source MAC address, and the MAC address of PDC as the destination MAC address. It's okay?
So R2 doesn't have a forward table.
It has a forwarding table.
Okay, it has.
But I don't show it here. But here just I show the table of R1, but it has a forwarding table. And all devices in the network has a forwarding table.
Okay, so it will forward it to the correct LAN, and then within the LAN it will get the MAC address.
Exactly, yes. Exactly, yes. Now with the routers, sometimes we have a huge routing table. For machines that are at the endpoint, they don't act as a router, so they have small forwarding table. Mainly, it's only 2 lines. One line to indicate the local area network, and the other line is the default gateway that indicates that all packets that does not belong to the local area network should go through the router.
Okay, thank you very much.
Most welcome. Have a nice day.
Could you once again show the solution for C?
Sorry?
The solution for C, yeah, that one.
Yeah. Here,
okay.
Here we see we have 10-0, and we consider only the 13 first bits. That's why I wrote here only 13 first bits.
And the DNS server would have another byte at the 13th. The 13th bit of the DNS server is different, right?
Exactly, it's different. The 13th bits, the DNS server has the same here, but here it is 1010. So here we have 1.
Okay.
It's different. We don't have any match.
Okay, yeah, I just wanted to see that again to be sure.
Yeah.
Okay, thanks.
Most welcome. Okay, bye.